Welcome to the final video in this series of short videos on chemical relations and mass relationships in reactions. In the previous video, linked in the description below, we looked at gas phase reactions. Specifically, we looked at what was called the ideal gas law, where an ideal gas is defined as a gas that has no volume and no interactions. Essentially, a blank space filled with particles that contain no volume in and of themselves. Those particles do not attract each other, they do not repel each other, they are not attracted or repelled by the wall. This led to the development of what was called the ideal gas law, PV equals nRT, where R, the gas constant, had a value of 0.0821 liter atmospheres per mole degree Kelvin, and was a universal constant. This last fact is of some interest since every gas is chemically and physically different, yet they are described by the same constant. In this video, we'll look into why that is, how gases actually behave, and use a model that will go into some detail to come to some interesting conclusions. We'll be looking at a kinetic model. Kinetics is the study of particles that are in motion. In our case, the particles in motion will be gases, where once again, the gases are independently moving particles that have no interactions with themselves or with the surroundings, and therefore, any collisions they have will be elastic, meaning that the energy that goes into the collision with either the wall or another molecule will be the same as coming out. So, again, with some detail, let's look into what this means. Suppose I have a particle of mass m interacting with a wall in the YZ direction, and that particle is moving in the X direction. Force is described as mass times acceleration. The mass of the particle is given in kilograms. Acceleration is the change of the average velocity, symbolized by u with a bar over it, in the x direction, times the change in temperature, times the change in time, rather. Since I have an elastic collision, the change in velocity, u final minus u initial, the particle will move in and move out at the same velocity, but the direction will change. So the velocity in the final motion, moving back, will be equal but opposite to the initial velocity. Therefore, the change in velocity for the system will be minus 2 times the average velocity. Similarly, since I'm traveling over a set distance x, I can find the change in time. By definition, velocity is the change in distance with time. Therefore, the change in time is going to be the change in distance, which is x forward and x in reverse, or 2x, divided by the velocity. So, I put these things together and I get a force equal to the mass times the change in velocity with the change in time, with the change in velocity being minus 2 times the initial velocity, the change in time being 2x over that velocity, or the force equal to minus the mass times the velocity squared divided by the distance. If I want to look at pressure, pressure is force over area. So it's going to be, first of all, you lose the negative sign because the pressure is being felt by the wall, not the particle. So the force felt by the wall would be positive mass times velocity squared divided by x, divided by y, divided by z, or, in other words, the mass of the particle times velocity squared divided by the volume. That's for one particle moving in one direction. If I want to expand this, suppose I want that particle to move in 3 directions, free to move in either x, y, or z. All of these are independent, so the total pressure is simply going to be the pressure felt in the x direction plus the y direction plus the z direction, or the mass times the velocity in the x squared over volume, y squared over volume, z squared over volume. Since velocity is a vector, the total velocity is simply the magnitude of the total velocity. U squared is ux squared plus uy squared plus uz squared. So my total pressure now simplifies to the mass times the total velocity squared over 3 times the volume. You'll see why we're going through this detail in a few seconds if one wishes to bear with me, because now, let's say I fill this space with a number of particles, n, each free to move in any given direction. In this case, the total pressure is just simply going to be n times the pressure of any given particle. So it's going to be n times the mass of each particle times that particle's velocity squared over 3 times the volume. At this point, you may notice that there are some letters that are beginning to look familiar, specifically P and V. So I can rewrite this to say n times mu squared over 3 is equal to PV. However, PV is also equal to nRT from the ideal gas law. One substitution, so n number of particles times the mass of each particle times the velocity squared of the particle divided by 3 is equal to the number of moles of particles present times this gas constant times the temperature. Rearranging that, you get the following, where I have 3 times the moles divided by the mass of n particles, or in other words, 1 over the molar mass given in kilograms. So roughly speaking, the square of the velocity of the particle is 3RT divided by the molar mass in kilograms. Specifically, the velocity of any given gas particle in the kinetic theory would be the square root of 8RT divided by 3 times the molar mass. Why go through this lengthy discussion to get to this point? If one looks at units, velocity is in meters per second. The value of R that we know of liter atmosphere per mole degree Kelvin would not cover that. However, what this shows, velocity has kinetic energy in it. What R actually represents is the potential of 1 mole of any type of independently moving particles. This is why the value of R is universal and independent of the gas. As long as the material is in the gas phase, its movement will be independent. With this, several relationships can come forward that are going to be useful. First of all, one notices that velocity is directly proportional to the square root of temperature. Essentially, as one adds more energy to the system by raising the temperature, the particle will move faster. So if I have the same molecule at 2 different temperatures, the velocity at temperature 2 divided by the velocity at temperature 1 will be the square root of T2 over T1. Velocity is also inversely proportional to the square root of the mass. This also makes sense because if something is heavier, it's going to move slower. So as weight goes up, velocity goes down. So if I have two molecules at the same temperature, the velocity of B over the velocity of A is going to be the square root of the mass of A over the mass of B. This factor can be used analytically. As mentioned, heavier things move slower, so velocity is inversely proportional to mass. Velocity is also inversely proportional to time. The longer amount of time it takes something to move, the slower it's moving. You can combine those to say over a course of a set distance, the amount of time it takes for a gas molecule to move a set distance is going to be directly proportional to the mass. This is called effusion. In an effusion experiment, one has a cylinder with a piston on the end of it. At the end of each cylinder, a tiny pinhole is drilled. The cylinders are filled with gases, two different gases, one heavy, one lighter, call them A and B. And then the piston, which moves among a given distance, identical distance x, is pushed forward with an equal force. It's obviously harder to move the heavier gas than the lighter gas, so the piston will take more time to travel the same distance with a heavy gas than a light gas. And one winds up with Graham's law of effusion, that if one compares a known to an unknown, the time of A to the time of B is the square root of the mass of A over B. Using this with an example. Argon completes the effusion experiment in 4.11 seconds. Some unknown with a general formula SFX completes the same experiment under the same conditions in 7.85 seconds. You can use Graham's law to identify an unknown. In this case, you can find out what the element X is. For starters, the time that it takes the unknown to travel, 7.85, divided by the time it takes for the known, 4.11, will equal to the square root of the mass of the unknown, which is unknown, divided by the mass of the argon, which is known at 40 grams per mole. So the square root of the ratio of the masses is 1.91. To remove the square root, both sides are squared. You get some unknown is equal to the mass over 40, is equal to 3.65. In other words, the mass of the unknown is 40 times 3.65, or 146 grams per mole. That unknown contains one sulfur, which weighs 32 grams, and 6 moles of an unknown. That means 6 of the unknowns would weigh 114 grams. My unknown weighs 19 grams per mole. So the unknown is fluorine, and the unknown compound is SF6. So, in closing, all chemical relations come down to the relationship, the ratios between the number of atoms and molecules expressed in moles. How one finds this depends upon the phase. For a solid, one looks at the molar mass, how many grams are in 1 mole. For a solution, one looks at the concentration of reactant or product in how many moles per liter, the molarity. And for a gas, one has the ideal gas law where everything is a related variable, PV equals nRT. This is a universal law because a gas is a collection of independently moving particles and therefore follows the rules of kinetics. As we've seen, the value of R is universal because it expresses the energy of a mole of independently moving particles. This can be used experimentally to determine the mass of unknowns. As a matter of fact, Graham's law of effusion is one of the primary ways of determining the mass of a completely unknown compound. I hope you found this series of videos interesting and useful, and thank you for watching.